Good morning, boys and girls. Welcome to another lesson on Physical Sciences Grade 12. Today we are continuing with paper 2 and we are still continuing with organic chemistry. But today we are looking at the last section of this topic, which is physical properties. Remember, we started with nomenclature, then we looked at organic reactions, and today we are looking at physical properties. Furthermore, remember what I said. I said this topic counts about 48 to 60 marks of your paper 2. And it is very critical that you understand it well because we want you to get your distinctions. And hence, we are dealing with questions that are really dwelling deep into this section on physical properties for today. Right. Now, let us look at what your examination guidelines are telling us about physical properties, what we are actually supposed to know. Right. Remember, in grade 11, you learned about intermolecular and interatomic forces. So when we deal with physical properties, we are going to look at molecules and we will be identifying the types of intermolecular forces present in each and how these intermolecular forces influence the physical properties of a group of organic compounds. And those intermolecular forces will be the dipole-dipole forces. And then we will be looking at the induced dipole forces, which are the London forces. And then we are also going to look at hydrogen bonding. Now, we must be able as well to note the differences between intermolecular forces as well as interatomic forces. We are not supposed to confuse the two, but we are not going to look at interatomic forces in this section. We are just going to look at intermolecular forces. It's just that we need to ensure that we do not mix intermolecular forces with interatomic forces. And then we must be able to talk about the relationship between intermolecular forces as well as molecular size. Right? In other words, we must look at how the molecular size influences the strength of intermolecular forces. Furthermore, we must be able to explain the effect of intermolecular forces on the boiling point, the melting point, as well as the vapor pressure. And all of these, the boiling point, the melting point, and the vapor pressure are what we refer to as physical properties. Now, with every section, my dear learners, we know that we must be able to define the relevant terms. And the terms that we are supposed to define in this section is the definition of the boiling point, the definition of the melting point, and the definition of the vapor pressure. My dear learners, remember that definitions are low-hanging fruits. These are the definitions which you are always supposed to get right altogether. So you can't be losing marks when it comes to definitions. And you are required to only give these definitions that you get in your examination guidelines. And remember that the definition for boiling point, it is the temperature at which the vapor pressure of a substance equals the atmospheric pressure. So when the pressure of the vapor equals the atmospheric pressure, then you know that at that temperature, you have reached the boiling point. Furthermore, to define the term melting point, we know that as well it will be the temperature at which the solid and liquid phases of a substance are at equilibrium. Right, you must be able to give that. And lastly, under physical properties, we must be able to define the term vapor pressure. And that is the pressure exerted by a vapor at equilibrium with its liquid in a closed system. Now, one mistake that we often see as we mark you is that a learner would say it is the pressure exerted by a vapor at equilibrium with its liquid, and the learner would omit in a closed system. Remember, these definitions are 2 marks or nothing. In other words, if you omit any keywords in this definition, then you are going to lose all the marks. It will not be 1 out of 2. We go further. After a quick revision on physical properties, remember, you must understand the relationship between vapor pressure as well as boiling point. And we know that if an organic molecule has a high boiling point, then it will have a low vapor pressure. And the vice versa is true. In other words, if a molecule has a low boiling point, it means it will have a higher vapor pressure. In simple terms as well, the higher the boiling point, the lower the vapor pressure. Or the lower the vapor pressure, rather, the lower the boiling point, the higher the vapor pressure. Now, we must also understand the relationship between the strength of intermolecular forces as well as these physical properties, which is the boiling point, the melting point, as well as the vapor pressure. But we understand that the boiling point of a molecule depends on the strength of the intermolecular forces. And that goes as well for the melting point as well as the vapor pressure. They depend on the strength of intermolecular forces. Now, if the intermolecular forces are strong, it means the boiling point will be high. The melting point is also going to be high, but the vapor pressure is going to be low. Why is the vapor pressure low? Because the higher the boiling point, the lower the vapor pressure. In other words, if the intermolecular forces are strong, the boiling point is high, the melting point is high, but then the vapor pressure will be low. Putting it somewhat differently, but meaning the same thing. If the intermolecular forces are weaker, then the boiling point will be low, the melting point as well will be low, but the vapor pressure will be high. So we need to understand that. Now, we are going to look at different types of intermolecular forces as noted before. And those intermolecular forces, as I have mentioned them, are your dipole-dipole forces, your induced dipole forces, which we simply call the London forces, as well as hydrogen bonding. Right. And as we do the questions, you will see that it gets a little bit easier. Now, I want us to move straight to a question from previous examination papers. And this is a very nice question to deal with because it looks at all aspects in terms of physical properties. Now, it reads as follows. The table below shows the boiling point of 4 organic compounds represented by the letters A to D of comparable molecular mass. So let us look at our table. There's the 4 compounds A to D. It's butane, it's propanol, it's propan-1-ol, it's ethanoic acid. And the molecular mass is also given. And the boiling point of each organic compound has been given. And it is measured in degrees Celsius. Now we go to the questions. 19.1. Compound A is used as a fuel in gas burners. So butane is used as a fuel in gas burners. This is also one aspect that you need to know from the section on organic reactions, because butane is an alkane. It belongs to the homologous series alkanes. And we know the most important use of alkanes is that we use them as fuels. If we asked you, what is the most important use of alkanes? We'll say alkanes are used as fuels. So that is just the statement. 19.1.1. They say, is compound A in the gas, liquid, or solid phase at 25 degrees Celsius? It means we need to choose any of those states. So we need to go and look at compound A, which is butane, and actually try and check what is its phase when the temperature is 25 degrees Celsius. Now, when you go to your table there, you have been given the boiling points. And we know what happens when you have reached a boiling point. If you are an organic molecule, remember, when you have reached the boiling point, there is a phase change that occurs. And the change is that you are changing, right? Erase that. You are changing your phase from the liquid phase to a gaseous phase. So at the boiling point, you are now changing your phase from liquid to gas. In other words, butane changes its phase from liquid to gas when the temperature is 0 degrees Celsius. So when the temperature is 25 degrees Celsius, then it means this substance would already have been in the gaseous phase. Why? Because it became, or it transformed into a gaseous phase already when the temperature was 0 degrees Celsius. So at a higher temperature, like 25 degrees Celsius, then it is a gas phase. So the answer there must be a gas, and that must be for 2 marks. Our answer there must be a gas, and therefore we are only supposed to write a gas because there is no other phase beyond the gas phase. Now, we move to the next question, right? This was actually 1 mark. 19.1.2, how will the boiling point of an isomer of compound A compare to that of compound A? Write down higher than, lower than, or equal to. And we are required to refer to molecular structure, intermolecular forces, and the energy needed to explain the answer. Now, compound A is butane. Now, let us answer the question. Now, firstly, butane looks like this. But means we have 4 carbons. 1, 2, 3, 4. Then I'll put my hydrogens, making sure that around each carbon, I have 4 bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It means butane, it's C4H10. Now, this is compound A. Now, an isomer of compound A, you will remember we talked about this. We said isomers are organic molecules with the same molecular formula, but different structural formula. It means an isomer of butane must also be a C4H10. It must be a C4H10 because the molecular formula has to be the same, but the structural formula has to be different. And we know when we deal with alkanes, when we want to make isomers, we have to make chain isomers. And when you make chain isomers, what you definitely do is you reduce the size of the parent chain. You will first start with 1 carbon so that you make it a branch. So what we'll do is I will say 1, 2, 3 carbons. And therefore, now I'm short of 1 carbon because I have reduced the size of the parent chain. It is no longer a but, it has 3 carbons, it is a prop. So instead, I will then take 1 carbon and make it a branch so that I make a methyl substituent. Then I put my hydrogens to make sure that around each carbon I have 4 bonds. H, 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 and there are my hydrogens. There are my hydrogens. Right. Now, if you count the hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are 2 organic molecules with the same molecular formula, but different structural formula. And therefore, this is the isomer. Now, when we want to deal with this explanation of why these 2 molecules might be having different boiling points, as asked in the question, say which one of the 2 between the isomer of compound A being compared to the actual compound, which is A, how will the boiling point compare? Then I will say, okay, by just examining the isomer of compound A, I can see that the isomer of compound A, the parent chain has 1, 2, 3 carbons. But when I look at A, the parent chain has 1, 2, 3, 4 carbons. In other words, A has a longer parent chain, but the isomer has a shorter parent chain. It means the chain length of A is longer and the chain length of the isomer is shorter. And we know that the longer the chain length, the higher the boiling point. The shorter the chain length, the lower the boiling point. In other words, the boiling point of the isomer is going to be lower than that of A. So this one, which is the isomer, its boiling point will be lower compared to what? Compared to compound A. And that's where we get the first mark. And now we are required to give an explanation. And we were told that we must refer to molecular structure. So write this in a bullet form, right? Don't write paragraphs because that is going to make you write a long paragraph and in between you start to make mistakes. So in terms of molecular structure, what we are going to say is we are going to look at the two structures. And what is different about these structures is definitely the chain length altogether. So we are going to say the chain length of the isomer is shorter than that of compound A. So we can see it is shorter. And what is actually shorter? Remember, when we are referring to this chain length, we are referring to the parent chain, the longest chain without breaking. So the chain length of the isomer is shorter than that of A. And then we were required to talk about the strength of intermolecular forces. So the strength of intermolecular forces. Right? This is the second bullet. This was the first bullet. This is now the second bullet. Now we know A, because it has a long chain length, it means the intermolecular forces are strong. The isomer, because it has a short chain length, it means the intermolecular forces are weaker. Then I am going to say the inter. Okay, let me do it this way. Intermolecular forces of the isomer are weaker than that of A. And the last one, we are required to refer to energy. Now, if the intermolecular forces are strong, it means we'll need more energy to break the intermolecular forces. If the intermolecular forces are weaker, then we'll need less energy to break the intermolecular forces. Then I'm going to say energy needed to break the intermolecular forces, the energy that is needed, or preferably, if you don't want to use the word break, you can use the word overcome to break the intermolecular forces of the isomer is less than that required or needed to break those of A, which are the intermolecular forces of A. All together. And this is how you would have got your first mark, the second mark, as well as the third mark. Common mistakes that we see here is that learners, instead of talking about intermolecular forces, they will be referring to bonds. We are not talking about bonds here. We are talking about intermolecular forces. Now, we move on. These ones we have already answered, 1911, 1912. Now we move to 19.1.3. They're asking us, using molecular formulae, write down the balanced equation for the combustion of compound A in excess oxygen. Now, you will remember, right, that an instruction has been given here, and they are saying you must use molecular formulae, and we must show complete combustion of compound A in excess oxygen. We've already written the molecular formula for compound A, which is butane. It's C4H10. And butane, it is undergoing a combustion reaction. It means it reacts with oxygen gas. So those are my reactants already there. I have 1 mark. And then my products will always be carbon dioxide and water reacting in excess oxygen. And then I have to balance. Now, if I have to balance here, my dear learners, I just want to give you a trick. When you deal with combustion reaction, and it is combustion reaction of organic molecules, once you note that you are dealing with an odd, rather with an even number of carbon atoms there, automatically just put a 2 next to the organic molecule. When you are done with that, then you start to balance. And you balance first the carbons, then the hydrogens, and then the oxygens, and then it will be easier. The number of carbons on the left, it's 2 times 4, which is 8. And therefore, I also need to have 8 on the right-hand side, which is the product. And I'm going to put an 8 there. Remember, we do not balance there, because when you balance there, it means you are changing the substance. Right. So every time when we balance with stoichiometric coefficient. In other words, we put the mole ratios there. Then the carbons are balanced. Then the hydrogens, it's 2 times 10. In the reactants, it's 20. Then in the products, I also need to make it 20. So I'm going to put a 10, because 10 times 2 will give me a 20. Then for the oxygens, on the left-hand side, which is the reactants, I have 2. But on the right-hand side, I have 8 times 2, which is 16, plus 10 times 1, which is 10. In total, my oxygens in the product is 26. And therefore, I need to balance in the reactants. And to make this a 26, I'm going to put a 13. So 13 times 2 will give us 26. And it is balanced. Now we've been asked again in 19.1.4. Compound A has a lower boiling point than compound B. Give a reason for this difference in boiling points by referring to the structural differences between the two compounds as well as the polarity. So now I'm dealing with butanal as well as propanal. Right. Now, rather, I'm dealing with butane as well as propanal. Now, we know that when we are dealing with butane, we are dealing with an alkane. And when we are dealing with propanal, we know that we are dealing with an aldehyde. Are we together? Now, when we want to explain why the boiling point of A is lower compared to the boiling point of compound B, we are going to refer to all these headings that have already been given to us. Now, we must talk about the structural differences. So, in your structural differences, it will be your first point. So, you will then say A, because we already know it's butane, is an alkane. And if A is an alkane, then we know that it only has London forces. And B is an aldehyde and contains dipole forces in addition to London forces and has dipole forces and has dipole forces in addition to London forces. Right, so the difference here is that when you are dealing with A only has London forces, but when you are dealing with B, which is an aldehyde, it has dipole forces in addition to London forces. And therefore, in terms of polarity, then we know that A is non-polar. A is non-polar and has weaker intermolecular forces intermolecular forces compared to B. Compared to B, which is polar right. And this is how you would have had all your marks. And remember, they already told you that A, its boiling point is lower than that of B. In other words, the intermolecular forces of A are weaker compared to the intermolecular forces of B, and A is nonpolar while B is polar. Right. Then we go to the next question, which says, consider the boiling point of compound C and D. Now, let us look at compound C and D. Compound C and D, propan-1-ol, as well as ethanoic acid. Give a reason for this difference in boiling points by referring to the intermolecular forces present in each of these compounds. Now, my dear learners, to always be on the safe side, even though they said you must refer to intermolecular forces, you must actually explain holistically all the reasons that makes the boiling point of these molecules to be different. So firstly, you were told that you must refer to intermolecular forces. Intermolecular forces. So we know that C, it was propan-1-ol. C was propan-1-ol. And then we know that D was ethanoic acid. Then we are going to say, remember, both C and D have hydrogen bonds. Remember, my dear learners, when we learned intermolecular forces, we know that for our purpose in organic chemistry, only alcohols and carboxylic acids have hydrogen bonds. So you're going to say both C and D have hydrogen bonds. And this is the easiest way that you can write it. So now we have referred to intermolecular forces. But now, if C and D both have hydrogen bonds, why are the boiling points then different? It means we need to explain further. Now, from the table, we can see that the boiling point of ethanoic acid is higher than the boiling point of propan-1-ol. In other words, I can then conclude that the intermolecular forces in the next bullet, the intermolecular forces of D the intermolecular forces of D are stronger than the intermolecular forces of D are stronger than that of A. How did we see that? Because the boiling point of G is stronger than the boiling point of C. So the intermolecular forces of G are stronger than those of C. And now we get surprised as to why would they be stronger than those of C if they're both hydrogen bonds. And this is where you remember that C, because it's a carboxylic acid, it has D, because it is a carboxylic acid, it has two sides for hydrogen bonding, and C is an alcohol and it only has one side for hydrogen bonding. And therefore, we are going to say this is because D has two sides for hydrogen bonding, and C only has one side for hydrogen bonding. Right. Then we know that the energy, and this is the next point, needed to break the intermolecular forces of G is greater than the energy needed to break the intermolecular forces of C. So the energy needed to break the intermolecular forces of G is higher than the energy needed to break the intermolecular forces of C. And how do we know that? Because the intermolecular forces of D are stronger than the intermolecular forces of C. And hence we need more energy to break down the intermolecular forces of D as compared to C. And remember, if you are not used to using the word break and you are used to using the word overcome, it basically means the same thing. And the last question for the day, it reads as follows. Which one of the compounds C or D has a higher vapor pressure? Refer to their boiling points to give an answer. And we know the answer there. It must be C. Why? Because it has a lower boiling point. Remember what we said. We said the higher the boiling point, the lower the vapor pressure. If the boiling point is high, it means the vapor pressure is low. And if the boiling point is low, it means the vapor pressure is high. When you look at C and you compare it to D, you will see that C has a low boiling point. In other words, it then has a higher vapor pressure, and that will be your next mark, because this is where we are looking for the reason altogether. Right, and that really marks the end of the lesson for today. Remember, my dear learners, this section is very important. You must know your definitions. You must know how to relate the relationship between physical properties and the strength of intermolecular forces, the energy that is needed to break those intermolecular forces, the types of intermolecular forces that are present in the organic molecules that you are also dealing with. And also, as you answer these questions, ensure that you avoid working in a paragraph format when you explain why the boiling point of one molecule differs from the other, because in between it loses meaning and it ends up not making scientific sense. And therefore, I'm encouraging you to use it in a bullet form, because the bullets are also marked independently. And thank you so much again for tuning into the lesson. Your hard work is definitely going to pay off eventually. So thank you so much. I will see you next week when we deal with a different topic in physical sciences, as we prepare you for your preparatory examinations as well as your final examinations. Thank you so much and enjoy the rest of the afternoon. Bye.